That's an Arduino Nano version 3, to be exact 3.3 if you believe what's printed on its back. And this is the, well, still new Arduino Nano Every. Question is, should every Arduino Nano be an Arduino Nano Every or not? I will try to answer that question, at least for me, in this video, and as always, I will go into the details. I'll have a close-up, very close-up view on both boards and compare them. I will also compare their official specs. And I will try to run a little program that uses a bit banging library I wrote for the V3 on the Every. Finally, I will utilize the onboard switch mode 5-volt regulator on the Every in a way that's basically impossible with a linear 5-volt regulator on the V3. And then we shall draw our conclusions. Let's first have a close-up of both boards. The elephant in the room, of course, there is an ATmega 328 on the Nano version 3, while on the Nano Every there's an ATmega 4809. They do have different USB connectors. One is mini, the other is micro, or the other way around. Point is, you need different USB cables to connect them. The Nano Every still has 4 LEDs like the Nano V3. Yeah, 1, 2, 3, 4. Just very tiny and spread over the board. Yeah, you have here 1, 2, that's an LED, 3 and 4. Did I mention there are reset switches on both? And yeah, more important, there is no ISP header here on the Nano Every. For the next few parts I had to turn the poor Nano V3 on its back, and there we see first the 5-volt linear regulator, which has been replaced on the Every by a switch mode buck converter. That's important, and I will come to that back later. Also, the FTDI serial to USB interface chip is gone and has been replaced by another, I don't know, PIC microcontroller also, which they programmed by themselves. And by the way, I think that's a 3.3 linear regulator on the Every. Now the Every, it's on its back, and you see here 1, 2, 3, 4, 5, 6 gold-plated pads, which are not an ISP interface, but a UPDI, Unified Program and Debug Interface. So this is not exactly pin compatible with the Nano version 3. Also of note, the back of the Every is completely clean. So without using pin headers, you can put that onto a board and solder it on by using these half moon pads here on the side. Aside from the programming headers, they are supposed to be pin compatible. So yeah, here the first row, TX, RX, RST, yeah, you see it. Ground, D1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And yeah, please note the labels on the Every are on the back of the board. So they'll do you... they do nothing for you, sorry. If you have that soldered in somewhere, or if you solder in a pin header and have it on your breadboard. And the other pin row, VIN, ground, reset, 5 volts, A7, 6, 5, 4, 3, 2, 1, 0, reference 3.3 volts and digital 13. On to the specs. I basically copied that from the Arduino website, and yeah, some lines or some data were not given for the Nano V3 and vice versa for the Every, and there I have some, yeah, additions of mine in italic or in handwriting. Anyway, I already mentioned that the Every has an 80 mega 4809 and the Nano V3 an 80 mega 328. Both run at 5 volts. Both can be powered via their USB ports or via their V-in pins, and there the input voltage limit for the Nano V3 is 7 to 12 volts. Yeah, remember, linear regulator. While for the Nano Every in the datasheet there is an upper limit given of 21 volts. And what I could glean from the datasheet of the switch mode buck regulator here on the Every, the lower limit should be about 8 volts. The 3.3 volt pin of both should supply 50 milliamps, but for the Nano V3 I more or less guessed that, okay? Now for the interesting stuff. The clock speed of the Mega 4809 is 20 megahertz, while the Nano runs with its Mega 328 only at 16 megahertz. CPU flash memory, you have 48 kilobytes, that is 16 kilobytes more than the 32 kilobytes of the Nano. Also RAM, you have 6 kilobytes of RAM available in the Every, which is 3 times the amount you have in the V3 of 2 kilobytes. But EEPROM, if you are using that feature, the Every sports only 265 bytes, while the Nano has actually 4 times the amount, 1 kilobyte. And I totally forgot to mention that the DC output current per pin for the Every is 20 milliamps, while for the Nano V3, that is the 80 mega 328, it was 40 milliamps. But you have to take both numbers with a grain of salt, because other limits might apply. Yeah, refer to the data sheets of the processors. The Nano Every has 5 PWM pins, the Nano V3 6. Okay, and the rest is pretty much identical. Yeah, 1 UART, you need that for the USB port, 1 SPI, 1 I2C, and 8 ADC pins with 10-bit resolution. No digital to analog converters. If you want something analog out of these thingies, you have to go through the PWM pins. The Every can attach interrupts to all digital pins, while the Nano V3 was limited to 2. Length and width, we already seen that, is the same, 45 by 18. And the weight is, 5 grams for the Every, and for the V3, 7 grams. With headers, well, we will put that to the test. Anyway, the Every is programmed via the UPDI interface if you want to flash the thingy directly and not via the USB port, while the Nano V3 is using the ISP header here. Now let me solder in these pin headers to the Every and then play around with it a little. I've soldered in the pin headers, so let's do something with the Every. Here on the breadboard I have a Nano V3 that is a Chinese clone of a Nano V3 slaving away on driving 4 displays. So there's a little bit of my code and there's a bit banging library for these displays. If you want to know details, there were 2 videos about them. Yeah, 2 cards and 2 links below in the description. So let's try that. So I'm using the latest Arduino development environment 1.8.12, and here's my code. I'm using that TM6050 library, that is the TM60XX library. That's the driver chip for these displays. And now I will plug in the Arduino Every into the USB port and we'll see what happens. Okay, it recognizes the Nano Every. Okay, and it says, the Every is ready, but it says install this package to use the Every. So I just click that link, board for, I'm in the board manager. Okay, and it wants to install it, so we do that. Okay, so first steps with the Every, straightforward, but not plug and play. I would have expected that if I download the latest version of the Arduino development environment, that it would already, would have installed that, or would come with that package. Okay, you're allowed. No, I don't trust you every time. Okay, installed. Perfect. Let's see. And of course, my menus are German. No, this is not a Nano. This is a Nano Every. Nano Every. And it recognized the Nano Every. And I am on Nano Every, and I have... this is getting complicated, huh? I have an 80 mega emulation here, or I can do no emulation. This is just for the registers, but let's try it first with the registers emulated for the 80 mega 328. So first I compile it, and it says no babu. Oh, okay. So obviously my library has gone while I updated my Arduino environment. Give me a second. So after some changes to my code, obviously you cannot longer write B000 for binary, but you have to write OB. And updating all my libraries, it compiled at least, okay? But I get a warning here that the 80 mega 328 register emulation is enabled and I may encounter some speed issues. That's okay for the moment. We will try it to run without the register emulation and a second attempt, but for now let's try to upload that. Cannot find. Oh, come on. This is getting annoying. Okay, because we are on COM4. Why is he going to COM14? Okay, COM4, Nano, emulator. Raw. Do it. And I get, okay, he says he's finished, but he says cannot locate flash and boot memories in description. I don't know. I really don't know. Anyway, let's drop in that Arduino and see if it works. Despite that last error message in red when uploading to the Every, it seems to work perfectly. Okay, that's good. And yeah, you notice the difference. That is an Every because yeah, the LED that's blinking or yeah, that's illuminated is no longer here. But that little thingy here right beside the USB port. Okay, let's try it without the register emulation because yeah, there was a warning too. You might encounter speed problems. We'll see. Okay, let's try the same without the register emulation. Okay, compile it first maybe, just to be on the safe side. Okay, compiled without no warnings. That's good. Upload it. Yeah, there's that AVR dude message again, but let's see if it works. And it also works without that register emulation. So, at least for the TM16XX library, I'm golden. We'll definitely try out other bit banging libraries with the Every in the future and see if they are compatible. A major difference between the Every and the V3 is the onboard 5-volt regulator. In case of the V3, that was a linear type LM1117. And now on the Every, we have a switch mode step down converter, to be exact, an MPM3610. And this is really a beast. Yeah, according to the features, 4.5 volt to 21 volt operating input range. Remember, it's a step down converter, so you won't get 5 volts out if you put 4.5 volts in. 1.2 amps continuous load current. But of course, these are maximum values and we have to dig a little bit deeper into the datasheet to see if that little switch mode regulator here can actually fulfill our application requirements. And just as an example, I'll take my 4 displays I had on the breadboard. They draw a little less than 400 milliamps, so I need an output power of 5 volts times 0.4 amps. This is 2 watts. And then we have in the datasheet this diagram here, efficiency versus load current for output voltage 5 volts. So at 400 milliamps, we are at 2, 3, 4 at this line here. And for input voltage of 8 volts, we would have an efficiency of about 90%. And for input voltage of 12 volt, you see the higher the input voltage, the lower the efficiency. For 12 volts, we would end up at about 85%. Now, if I'm not running my board via USB, I want to run it via a 9 volt power supply. So I guess my efficiency is somewhere between 90 and 85%. So the 2 watts I need at the output divided by 85%, yeah, worst case efficiency, gives me I need an input power of 2.35 watts. And at the same time, yeah, difference 2 watts, 2.35 watts, I have a P loss of 350 milliwatts inside that little regulator. And I need to feed in 2.35 watts at 9 volts. That is only 261 milliamps. And that's something, 350 milliwatts power loss, that this chip can easily handle. Yeah, there are other diagrams here, but I digress. Yeah, in comparison, if you take a linear regulator, you want 400 milliamps out, you have to put 400 milliamps in. And at 9 volts, that is, you put 3.6 watts in. And that means, yeah, 5 volts times 0.4 amps, 2 watts, you have a power loss of 1.6 watts in my application example. I'm now in the data sheet for the linear regulator of the Nano V3. That's the Texas Instruments LM1117. And the maximum junction temperature for that thing is 150 degrees C. And the diagram I will use later is assuming ambient temperature of 25 degrees C. So we have a temperature budget of 125 degrees C. Yeah, divide that by the 1.6 watt power loss we would have feeding that thing 9 volts, 400 milliamps. We need to have a maximum thermal resistance of 78 degrees C per watt. And now if you look at that diagram here where they give you the thermal resistance in dependency to the copper area where that thing is soldered on, you see that, yeah, 78 degrees C, this is a little below that 80 degrees C line. And yeah, best case, that is all top copper where that thing is soldered on, we would need an area of a little below 0.4 square inch. Just to give you an idea what 0.4 square inches are, about the width, yeah, of the Nano as a square. And you see, there's no way in hell that this linear regulator has that much copper area, okay? And even if it had, that much copper area here, a square with the width of the Nano, which it doesn't. 25 degrees C ambient air is a fantasy because, the regulator is on the back. And if you put that in into a breadboard, you have here maybe 2.5 millimeter gap where air can circulate. So no way that regulator would survive that kind of treatment. Theory is one thing, praxis another. So I have here a 9 volt power supply, a simple switch mode AC to DC converter. No more USB power for my Nano Every. And I'm jumping over here to the ground and to the in pin. And everything is hunky-dory. It runs. Okay, my 9 volt rail from here is at 9 volts. And my 5 volt rail over here is at 4.8 volts. It's all a wee bit noisy, as you can see. So my 5 volt rail has about 600 millivolts peak-to-peak noise, and you see this is really high frequency noise from the switching. And my 9 volt rail has about 800 millivolts switching noise. Maybe we can improve on that. But before I try that, let me have a touchy-feely here with the switch mode regulator, and it's noticeably warm, but it's absolutely far from being hot. So we're golden. And just a talk putting two 470 nanofarad capacitors here in the circuit, one at the output of my 9 volt switch mode power supply and one here on the 5-volt rail of the Nano Every, took care of most of the noise. So at the 5-volt rail, we are now at, 400 millivolts peak to peak, and the 9-volt rail is about at 500 millivolts peak to peak. Yeah, you can improve on that, but for digital circuit, that's absolutely okay. To summarize, will a Nano V3 program run on a Nano Every? In my case, using one bitback library, it did. However, we saw that in red text the warning error message at the end of the upload to the Every. So maybe the integration of the Every into the Arduino development environment is not perfect yet. Are there cases where you can't replace a Nano V3 by a Nano Every? Yes, there are. If you need to supply it with an absolute minimum of 7 volts, I strongly suspect that's not possible with the Every. There you need 8 volts, and I derive that from the fact that in the data sheet of the switch mode generator on the Every, in the diagram we have seen, the lowest voltage they give for 5-volt output is 8 volts, and 8 volts has the best efficiency. So if that thing would run on 7 volts with 5 volts output with even better efficiency, they would have put in the curve here, just for sales reason. Other no-goes for the Every. You need 40 milliamps output on an I/O pin. Well, possible. You need a larger EEPROM of 1 kilobyte. 265 bytes is not enough. Or you need all PWM pins, all 6 of them. Where does the Every shine? I mean, for my special application, obviously the onboard switch mode raw voltage regulator. That's a big plus. You can do things with that you simply cannot do with the linear type regulator on the Nano V3. You got 25% more clock speed, you got 50% more flash memory, and you got 200% more SRAM. And you have interrupts on all digital pins. To be honest, I don't know what I should think about the change from ISP to UPDI. Software-wise, probably not a problem, but mechanically, contacting these UPDI pads on the back of the Nano, a bit fiddly, and if you actually solder that into a board, don't forget to leave a cutout here in the board so you can access the pins. Last but not least, the Every is cheaper than the V3. So official price for V3 is about 20 bucks, and a single Every, I think a little less than 10 bucks. You can get 3 packs for 22, 23 bucks. But keep in mind, you can still get Chinese Nano V3 clones for just a few bucks. And I mean a few bucks. $1.99, $2.99, $3.99, whatever. So, is the Nano Every the better Nano? I'd say in almost every aspect, yes. And I will definitely switch over to the Nano Every for my everyday development. And with that conclusion, I say bye.